So today what I want to do is discuss the concept of statistical power. Specifically, what is it and why does it matter to researchers and why does it matter to people who are communicating science to the public? Now, statistical power, unfortunately, is an abstract concept. Does anybody here play with power ideas or statistics more generally? It's kind of fun. So I want to kind of break it down with a concrete example just to sort of get us rolling. Now, I'm an instructor. I teach in the Department of Psychology, and like many of the people in this room who are teachers, there's probably one thing that drives you absolutely crazy. Is it this? I see my colleagues tweeting right now as I speak. Now, we have a lot of concerns about the role of devices and laptops and technology in the classroom more generally. One of our concerns, of course, is that students become automatons when they're trying to use their laptops to listen to us teach in classrooms. They begin to just type whatever it is that we're saying without fully processing it. Of course, another concern we might have is simply that they find their devices much more entertaining than us. And if you're kind of insecure like me, that makes you really uncomfortable, okay? But the truth of the matter is, we don't really know a whole heck of a lot about how the use of laptops or how the use of technology in classrooms may impact student learning. But this is the part where research methods becomes really cool. Because if you're a psychologist like me or somebody working in the social behavioral sciences, you say, aha, let's do an experiment. Let's get some students, and we'll randomly assign, let's say, 20 of them to use laptops or devices in classrooms, and then we'll have the remaining students not be allowed to use laptops or devices in classrooms, okay? Maybe we'll have 20 students in each condition. And then at the end of the semester, what we will do is simply study people's grades, and we'll see whether those grades differ across these two groups, okay? What a great way to find out whether this stuff really matters. Now, keep in mind, all this is sort of a mechanism to make the concept of statistical power more concrete. I don't want you to get caught up in the details of whether final grades are a good measure of student performance, things like that, okay? They come to me at the end of the semester saying it's the most important thing in the world, so I'm pretty sure it is. Now, let's say these are our results. We find out that the average grade for people who had devices throughout the course of the semester was about 70.2, let's say on a 1 to 100 scale. And in the no devices condition, it's closer to 71. Okay, so we would say that this is about a 0.8 difference. And just as an aside, in psychology and other social and behavioral sciences, we like to express this in a form called effect size metrics. So in other words, we take the difference of interest and express it relative to the variation in the scores. So in this case, we would say there's a Cohen's d of 0.08. One group is about 0.08 higher than the other. Now, this is interesting news, right? If you're concerned with whether the use of devices in the classroom might impair or facilitate learning, these data would seem to suggest that not having the devices would be a good thing. But for those of you who are in the sciences, you might know that we have to report a statistical significance test to draw any kind of conclusions from this that our colleagues will accept. And in this particular example, our p-value is not less than 0.05. So this is not a statistically significant difference. So what do we do in this situation? We have this joke in the social sciences. We bury this stuff. Nobody's going to be interested because we did not find a significant difference between the two groups, giving rise to what's called the file drawer problem. Now, here is the big question that confronts us when we're trying to understand what statistical power is. Namely, was the study capable of detecting a difference between these two groups if such a difference truly exists? Now, this is kind of a philosophical question in some ways, but we can address it statistically by playing a game. Now, I'm not good at equations, so anytime it comes to statistics, I start playing games. So this is how I confront these problems. Let's create a simulated world, okay? We're gonna have computational students who, in one group, have devices or laptops that they use in the classroom. And let's say because we're playing a game, we get to be God. We know what the truth of the matter is. And we're saying that in this condition, the actual performance is 70% at the end of the semester, okay? That is a fact, okay? That's the way we are creating this world. And we're gonna have another condition where students do not have laptops or devices. And in this world, the average final grade is about 75%. If we go back to thinking about effect sizes or differences between groups, this is essentially a 0.5 difference in terms of Cohen's d. One group is half a standard deviation higher than the other. So this is the truth of the matter. But what we're going to do now is draw random groups of 20 from each of these two conditions and find the average final grade for students in those conditions. So we might pull out one group and find that the average final grade is 68%, and then in the no devices group, it's 74%. So a 5-point difference, Cohen's d, 0.56 or so, not a statistically significant difference. Now, here's the important part of our simulation or our game. We're going to do this over and over and over again, because what we want to do is get a sense of how often we would detect the difference using this particular research strategy. So if we pull out another group, we find a somewhat small difference, 0.11, not statistically significant. We do it again. This time, we find a difference of 0.68 between the two groups, okay? Having a laptop impairs performance relative to not having a laptop, statistically significant. And we can continue to play this game over and over and over again. In fact, when we play these games in our lab, we do this about 100,000 times, okay? Does anybody want to go through all those results? No, okay. But here they are. The question we're asking here is how many of these 100,000 simulated results are statistically significant? Anybody want to take a wild guess as to what the answer is? That's correct, 34%. Sorry. Okay, so let's return to our original question. Was the study capable of actually detecting a difference if a difference truly exists between these two groups? The answer turns out to be is this study is capable of detecting that difference about 34% of the time. Now, this is the heart of what it means to discuss statistical power. Statistical power is defined as the long-term probability of detecting an effect if that effect truly exists. Okay, so when we translate this into our specific example, what we would say is the power of that study, where we have 20 people from this group and 20 people from this group, and we're comparing their average performance in a semester, is 34%. We'd expect that study to give us the correct answer 34% of the time. Now, although this is a fictitious example, I want to be clear that the outcome is designed to emulate what we know to be true about real research in the social and behavioral sciences. So this is a table that sort of estimates what the statistical power is of studies that are conducted in the social, behavioral, and medical sciences. Now, it turns out that for studies that have what we might call relatively small effect sizes, Brent Roberts is going to talk a little bit more today about exactly what that means. The typical power of those studies is about 15%, okay? So worse than our 34% example. For studies that truly have medium-ish effect sizes, so effect sizes comparable to a Cohen's d or half a point difference, the power tends to be about 50%, okay? And for studies where you're essentially trying to figure out if birds fly in the sky or walk on the ground, where the effect sizes are huge, we usually have no problem being able to detect whether those effects are real. Now that you know a little bit about what statistical power is, you can kind of wrap your head around it. I want to talk about reasons why statistical matters for researchers, why it matters for journalists, and why it matters for consumers of research. In particular, I'm going to talk about 3 different ideas. The first idea I want to discuss is that statistical power represents the fidelity of the study. That is, whether it is capable of getting the answer right. So when I say the statistical power of our laptop study is 34%, you can translate that in your head as saying, this study is only going to give us the correct answer 34% of the time. That's probably not a very good rate of success, depending on what your goals may be. Now, how many of you in here are actual researchers who have invested time in doing dissertations and things like that? Okay. Now, some of my students have designed really complex dissertations. We did some power calculations, and we found that the power of their study was about 40% or so. Now, why is that depressing? How many of you like to gamble? Brent Roberts, yeah, a few of you. I'm kind of intrigued by gambling, too. I'm holding in my hand a quarter. I have a 50-50 chance of getting heads when I flip this coin. that means this coin is in a better position to give me an accurate answer to the research questions I'm asking than the typical study conducted in the social and behavioral sciences. Now, if you're interested in cost-saving measures, give every researcher a quarter and don't educate them about power, and everybody wins, okay? An important thing to understand is that power is critical to discovering the things that we want to discover. So if we're not calibrating our studies to have high power, then we're not doing the best kind of research we can to answer our questions. Now, there's another side of this that I think is important, and sometimes important in a sneaky way. We don't always just want to know whether something matters or not. Does using laptops impair or improve learning? We want to know how much. And it turns out that low-power designs can be insidious for dealing with this issue as well. Now, this is something that we call a sampling distribution in statistics. So if we go back to our original study design, this would capture all the different results we would get if we were to draw those samples over and over and over and over again from a population that really differs by a Cohen's d of 0.5. I've illustrated that by the dashed line here. Now, as you're aware, we can only typically publish things in the social and behavioral sciences if we get statistically significant findings, which means out of this sampling distribution, about 76% of what all the studies that could have been done wouldn't have been published. So what remains are the statistically significant findings. Now, what happens here turns out to be really interesting. What if we were to take the average effect size among all the findings that were statistically significant? That is, average all these Cohen's d's for the significant findings. We'd find that the average effect size is 0.87. Notice that it is considerably higher than the true effect size of 0.5. We would call this an M error or a magnitude error. Specifically, due to the low power of our study, we are inadvertently overestimating the quantity that we're trying to estimate accurately in the first place. And that's doubly a problem, given that we probably were unlikely to get a significant result to begin with. If we do get the result, we're going to overestimate the effect almost by definition. Another problem here, which is a little bit more subtle because I'm not that good at making graphs, is we are also vulnerable to sign errors. Okay? These are errors where the effect is in the wrong direction. So remember, we were playing God when we did that simulation. We know that one group is half a standard deviation higher than the other. But in 1% of the research findings that are statistically significant, we're going to have a result in the opposite direction. And notice that the average of those findings is huge, negative 0.65. So if you ever wonder why there are competing findings in the literature, in underpowered literatures, this is exactly what you might expect to find. Now, the good news here is each of these findings is minimized when statistical power is high. So here's the same kind of sampling distribution, but under a situation where instead of having 20 kids in each group, we have maybe 100 kids in each group. Notice that this distribution is much more compact. That is, on average, we're getting the effect size estimate more correct than we would in the other case. Notice also that if we average all the effect size estimates together, we'd get an answer, 0.52, that is very close to the truth. And notice that in this situation, there are no sign errors. There are no studies reporting a significant result in the opposite direction of the truth. So to summarize the first point here, if devices impair learning, we might not be able to detect that effect if we're using low-powered studies. If we do get a significant result, we will likely overestimate the magnitude of the effect. And if we do get a significant result, we will run the risk that the results will actually go in the opposite direction of what happens to be true. Okay? So the first big thing to understand about statistical power then is it impairs our ability to get the answer right when there's something real there to be discovered. Now, there's a second problem that I think is a little bit more subtle. If you've learned about statistical power in the past, part of what I've told you already should be familiar to you. What I'm about to tell you will probably rock your world. Because when I learned about it about 3 or 4 years ago, it completely changed the way I thought about research design. In introductory statistics classes, we typically learn that alpha, a value set to 0.05 or so, is essentially the type 1 error rate of the study, what we might call the false positive rate. So whenever we're doing research and we're using significance tests, there's always some chance we're going to get a significant result when we should not have, when there is no difference between the two groups, when what kind of device you're using doesn't matter, when the drug you're taking doesn't matter. And we typically control that by setting the alpha threshold to whatever type 1 error rate we desire, such as 5%, which is common in the social and behavioral sciences. Now, here's the thing that's tricky to consider. Is the false positive rate actually 5% in research literatures simply because any individual researcher sets his or her alpha value to 0.05? The sad truth here is that the answer is that the type 1 error rate, or the false positive error rate, can be much higher than 5% when researchers use underpowered studies. Now, let me give you again a sort of concrete or visual example of how this might work. Let's assume that we're dealing with a research area where there's 100 researchers doing 100 studies. So we have 100 studies altogether. And moreover, they're not all answering or addressing the same question. They may be all concerned with the role of technology in education and learning, but they're doing slightly different studies, testing slightly different hypotheses, et cetera. So let's assume that in this world, half of the hypotheses that researchers are testing are actually true, okay? And half of the hypotheses that researchers are testing are actually false, okay? So the way I'm illustrating this here is, let's assume that these reddish, pinkish boxes, which is a great way of imagining what a research study looks like, right? Okay, are false leads, okay? There is no difference between conditions in these studies. Whereas in the green case, there is an effect of technology on education or something like that. So there are real differences there to be detected, okay? Now, the important thing to understand is when we set our alpha rate to 5%, what that implies is that even when there's no difference between groups, occasionally we will detect one. We call that a false positive. And if we use an alpha threshold of 5%, that will happen 5% of the time. So in this box world, that means about 2 out of 50 or so, rounding down, will turn out to produce false positives, okay? We'll get a significant result when we should not have, okay? Now, false positives are undefined if there is actually an effect to be detected. So the question here becomes, among the studies where there is a true effect to be revealed, how often can we detect it? Let's go back to our original example. We'll assume that the power of these studies is 34%. So we expect 34% of the time we'll get a significant result when we should have. And in this particular example, that implies that about 17 out of every 50 studies or so will get a significant result. Notice that it's not all of them because our power is only 34%. Now, we put these two things together again, and we're going to combine it with a sort of computational sleight of the hand, if you will. It's called publication bias. We tend to only submit papers for publication if we get a significant result. Reviewers tend to only favorably evaluate the manuscripts if there's a significant finding there to celebrate. And typically, those things only get published and written about if there's a significant result. So let's take that to the extreme and drop out all the studies where there was no significant result. What that leaves us with are 2 studies that are false positives and 19 studies, or yeah, something like that, I can't do math, that are true hits. That means among this entire set of studies where a significant result was found, 11% of them, that is 2 out of this set, are false positives, not 5%. Okay? So in this literature, more generally, the false positive rate can be considerably higher than we might have assumed it to be. It's not just 5%. Here it's almost twice as much. Now, this is a problem for statistical power, because what happens if the studies instead had 80% power? Well, again, we're going to have 2 out of the 50 that are false hits, but among those, oops, sorry, not good at animations. Among those that are highly powered, we're going to find that most, or at least 80% of them are statistically significant. So if we take this whole set of significant findings, now only 5% of them, roughly, are false positives, which is closer to our assumed type 1 error rate. Okay? So to summarize the key ideas here, I'm going to skip ahead a little bit here. To summarize the key ideas here, the false positive rate in a collection of studies can turn out to be bigger than 5%. And power is absolutely critical to understanding how those false positive rates work. When statistical power of studies is high, the false positive rate in the literature is much closer to what we traditionally assume it to be, about 5%. But when researchers are consistently using underpowered designs in order to investigate the issues they're trying to investigate, not only are they likely to miss out on things, as we discussed previously, they're also likely to create a biased literature where much more of the findings are wrong than you might have expected, simply on the basis of the way you thought about significance testing previously. Okay, the third important thing to understand about statistical power has to do with the replication crisis, or the crisis of confidence in the social and behavioral sciences. As Jennifer mentioned at the beginning in my introduction, in the social and behavioral sciences, we're undergoing what some people have called a crisis of confidence at the moment. That is, there's a large number of studies that people have failed to be able to replicate. Studies that have been the foundation for certain areas of research, studies that have been publicized in the popular media and the foundation of trade books. Things that we thought were true basically have come to rest on a very shaky foundation. And this has made a lot of us wonder, what went wrong and what can we do differently to fix this problem? Now, there are many ways to go about fixing this problem, okay? But one of the things that we can do that is most immediately impactful is be concerned with statistical power. Statistical power is potentially one of the reasons why we're in this situation in the first place. Recall that statistical power is defined as the probability of getting a significant result if you should be getting a significant result, right? So if your studies are underpowered, that means it's unlikely that you're going to be able to get the result that you're looking for. Now, if you're working in your own lab, that's probably fine. You just keep trying over and over again until you get what you're looking for, right? But let's say another lab comes along and says, we want to replicate the finding that just came out in Nature. Well, if they're using the same underpowered design that you used to replicate it, then the probability of them getting a significant result in a 34% power design is only 34%. Chances are they're not going to be able to reproduce your findings. Now, I'm not really good at math, so I made this cheat sheet. Let's assume that actually your study is as well powered as a quarter, okay? You have a 50% chance of getting the right answer if, in fact, there is a right answer to be found. That is a difference between conditions. So the first time you do the study, you have a 50% chance of getting the effect. The second time you or somebody else does the study, you have a 50% chance of getting the effect. So what's the probability of getting two significant effects with a 50% power design? It's pretty low. It's only about 1 in 4. What if 3 people are trying to replicate a study? It gets closer to about 10 or 12%. And of course, if you're lucky enough to have 3 people want to replicate your studies, the chances that they'll be able to do so, all 4 of them will be able to do so successfully, is as small as about 6%. Low power multiplies out to create very small numbers, okay? Anything less than 1 multiplies out to 0 eventually. But when you're starting with a low number, you are absolutely guaranteed to have a crisis of confidence, because underpowered studies simply are not going to be able to be replicated. Okay? You were lucky enough to get the result in the first place. The chance that somebody else is going to get the same kind of luck becomes diminishingly small. Okay. Now, there's a colleague down the street at Purdue, Greg Francis, who has used this logic to do something that I think is absolutely fascinating. Namely, what he's argued is that if you look at a lot of the research literature in the social and behavioral sciences, what we tend to celebrate and what tends to be highly prized in publication outlets are what are called multi-study packages. So in my home field, social and personality psychology, a typical article doesn't just contain 1 research study. It might contain 4 to 6, depending on how ambitious the authors may be. So it appears that in that package of studies, you have robust, reliable, replicatable findings, right? 6 different studies, all showing the same thing, okay? But what if they are underpowered studies? I just showed you that it's virtually impossible to get 6 studies that all converge on the same answer if you're using underpowered studies. So Greg Francis cleverly devised a test that allows one to detect how often you should get a string of significant results that converge on a single answer, given the statistical power of the studies. One of the things that he finds by surveying the journal Psychological Science is that about 82% of the studies or articles published in that journal present findings that are more robust than can be expected given the low power of the designs used. So there's a catch-22 here, namely, we know that low power is really bad for finding anything, much less replicating anything we find. And at the same time, some of the leading journals in our field are full of articles that purportedly reproduce and replicate everything that's been found. We know those things can't add up, and that contributes further to the crisis of confidence. So this is something important to consider when you're doing research or when you're evaluating research that you've been tasked with reporting on. Now, let me summarize the key ideas in this particular section. There are many factors that can contribute to replication failures. Nonetheless, in a field that uses underpowered designs, replication failures are essentially guaranteed. And the presence of multiple replications and underpowered designs can be indicative of publication bias and all kinds of things that might lead you to have a crisis of confidence. Now, I want to wrap up by discussing how can we go about designing well-powered studies, and how can you, maybe if you're a press officer or concerned with reporting on the literature, go about evaluating whether studies are adequately powered to report or provide us with reliable, robust information. Now, I'm going to nerd out just briefly, okay? Statistical power is considered to be a function of at least three things. One of the most critical things is what I called the alpha threshold previously, okay? We say that 5% of the time, maybe, we're willing to make a type 1 error. That is to reveal a significant effect when we should not have. That's something that the researcher typically clamps down, okay? But at least in psychology, everybody tends to use the threshold of 0.05 just to sort of keep things even. The second thing that matters greatly is the sample size or the number of cases that are used or colonies used in the research study in question. So as sample size increases in between subject designs, the statistical power of that design also increases. So this is what's commonly referred to as a power curve, and it shows how the statistical power of a statistical test varies as a function of the sample size used. And I've denoted on here the sample size of our original sort of laptop device study. Okay, if we have about 20 people per group with a Cohen's d of 0.5 and a sample size of 20 per group, our power is about 34%. Okay? But you can also see from this curve that if we were to increase the sample size, our statistical power would go up as well. So given that basic research design, we could, if we wanted our study to, let's say, be powered at 80%, that is an 80% chance of getting the answer right, if there's a real difference there, we could learn from this graph that we would need about 64 kids per group. Okay? That's not necessarily insurmountable, and having this information available to us can enable us to do better research design. Okay. Now, statistical power is also a function of what's called the actual effect size, or the population effect size. Now, Brent Roberts is going to talk about this a little bit in more depth later today, so I'm just going to brush over it really quickly. But what I want to say is that because statistical power depends on whether the effect size is, let's say, a half-point difference in your final grade, or a full-point difference, or a 10-point difference, clearly, the bigger the difference really is, the easier it is to detect it. Okay? So the way you think about power depends on how big you think that difference is. That is, what is a plausible effect size? The problem is, as researchers, we rarely know what the plausible effect size is. Okay? We're asking the research question typically because we're trying to answer that specific question. We might have some intuitions about how big it is, but part of the goal of the research is to estimate that quantity. Now, we can put some constraints on this. Oops, I'm running out of graphs here. There we go. Haha. Okay. There's one approach we can take here is to discuss what might be called plausible effect sizes. Okay, so in my field of social and personality psychology, based on people who do the hard work of summarizing studies of studies or meta-analyses, we know that a typical effect size is equivalent to a correlation of about 0.2 or Cohen's d of about 0.43. Okay? So we know that if people were just sort of reaching in randomly and studying some sort of research question, a good bet about what the effect size might be is a Cohen's d at 0.43. If we have that, if we're willing to use that as a working assumption, it tells us that, hey, we can use these power curves to make some guesses about what sample size we would need in order to have an adequate amount of power to design our studies well. Now, there is a caveat that goes along with this, namely because of the problem of publication bias and the magnitude errors that I told you about earlier. The things you see in the literature are almost guaranteed to be overestimates of what's really out there. So a good rule of thumb recommendation is to take something like this and cut it in half if you're designing your studies and you want to maximize the chances that you'll be able to reveal true things that exist. So, for example, we can use our power curves to sort of say, okay, if the population difference is actually comparable to Cohen's d at 0.43, which again is the standard in personality and social psychology, I know that with an n of 20, the power of my design is 30%. Okay? But I can sort of go anywhere along this curve. I can sort of change the sample sizes, and I can get better estimates of what kind of power I would need, or what kind of sample size I would need to have a better statistical power. The second way we can solve this problem is to say, what is the minimal effect size of interest? Okay? So one way to think about this problem is we don't know what the difference is, let's say in educational outcomes, between kids who are using devices and kids who are not. But we might want to be able to say, I want to be able to at least detect anything of, let's say, a Cohen's d of 0.5 or higher. If you can at least answer that question, it provides you with some guidelines for thinking about how to design the study, or alternatively, what kinds of studies are worth reporting on. Okay, so let me summarize some of the key ideas here. Power is a function of three things. The first is alpha, and I've put here load control, because what I mean is that researchers don't have a lot of control over this. That's not technically true. There are debates about how to adjust alpha in ways that are systematic, precise, and useful. But for the most part, people take alpha off the shelf at 0.05 and use that. Okay? So it's not something that you as a researcher typically control. Sample size is a critical ingredient in statistical power. And I've said here that researchers have high control over that. What I mean is that if you're working, let's say, in the social and behavioral sciences, you have a choice of whether to recruit 20 kids per condition in your study or whether to recruit 100 or 200 kids per condition in your study. Yes, using more cases requires more resources, but if the trade-off is to increase the chances of getting the answer right or getting a better chance of getting the answer right, it could be a trade-off worth making. And of course, population effect size. I said here that people have low to moderate control over that. What I mean is that I can't control, as the researcher, how much of a difference there really is between kids who are using laptops in classrooms and kids who are not. But there are some things I can do to control the effect sizes I'm studying. So I can use good measures that minimize measurement error, or I can use sloppy measures. The sloppy measures are going to make my study more underpowered than it would be otherwise. Or if I'm uncomfortable with studying questions that maybe require me to use underpowered studies, I might choose to focus on different questions. So as a researcher, I can choose to study obvious things or more subtle things that require more cases or more consideration of statistical power. Okay, so let me wrap up. Statistical power refers to the ability of a study to detect effects that actually exist. When power is low, not only are studies unlikely to reveal the truth, they can actually lead to false positives, sometimes at alarmingly high rates. When debating what kinds of studies we should be publishing or doing, or what kinds of studies we should be covering in the popular press, in my opinion, it is imperative that we consider the statistical power of the studies being considered. So I have sort of a set of questions that I think we can ask when we are considering whether to promote a specific research finding or studies that are coming out of a specific university or a specific lab. I think one important question a journalist or press officer can ask an investigative team is, what is the sample size that was used in this research? Under the assumption that sample size matters greatly for the statistical power of the results of the studies being conducted. Given this sample size, you can also ask, is the research well designed to detect the kinds of effects that might be expected in this area? Okay? So if you were considering writing about a study that has an underpowered design, and either you suss this out yourself or you ask some statistical experts, one thing to keep in mind is that it's unlikely that the findings of this study will ever replicate. It's unlikely that they've actually been able to detect some of the things that might actually exist in the background. And it could be very well the case that some of the things that they have found are false positives, because low-powered studies are more likely to lead to false positives. Finally, you should probably also ask whether publication bias is a potential problem in that field. I naively assume that publication bias is a problem in all scientific disciplines, but I realize that I just kind of exist in the fourth floor of the psychology department and have a very narrow view of the world. So an important question to ask is it possible that only significant findings are being incentivized in this particular research literature? Because if that's true, then that doubles all the problems that we're discussing today. Thank you very much, and I think we have a little bit of time for questions.
Thank you for the really great explanation of power. As somebody who teaches power, I'm over here.
Ah, what's up?
But your entire...
I hear voices in my head. Okay.
Good thing you're in psychology. The entire argument is based on this P less than 0.05, which some of us have identified as being a perverse incentive. Mm-hmm. And I was wondering if you could connect for people the relationship between power and things like precision and estimates that are outside of the realm of P less than 0.05 and statistical significance.
Yeah, that's a great discussion point. It's too bad that we're not drinking. Or have you been? Sorry. Okay, so there are two sides to that. Yes, I do think the whole, let's just call it a ritual. Let's be honest here. The ritual of significance testing has a lot of perverse incentives attached to it. When people, and students in particular, realize that they need P to be less than 0.05 in order to win or to get something that their professor will be impressed with, you create a system where students are motivated to get that particular outcome rather than get at the truth. And if the truth is something like laptops and devices don't impact student learning, we want to know that, right? We don't want to just know the things that work in the realm of significance testing. So the whole ritual itself creates all kinds of problems. It leads people to chase carrots when that's not really what they're supposed to be doing. Now, the concept of statistical power really only exists in the universe of significance testing. So it's part of this whole perverse incentives. It just happens to be the ignored part of it for the most part. But the key ideas play out even if you abandon significance testing. So for example, if we go back to our laptop example, one way we can frame the research question is less in a binary way. Do laptops matter? Do they impact student learning or not? We could say, to what extent does the use of technology in classrooms benefit or impair learning? We can turn it into a quantitative question. And then the answer there becomes that number that I'm showing you, Cohen's d, or whatever version of, whatever metric you choose to use. In that case, the same principles of statistical power apply. Namely, the larger the sample size, the more accurately you can estimate that quantity. So for example, the standard error gets smaller as the sample sizes increases. So the same principles still apply. Even if you were to abandon this ritual and say, you know what, P.05, that was for people growing up in the 90s. We are now an estimation generation. You still want to figure out what quantities are worth estimating and how you can estimate them well. And that requires careful attention to things about measurement and psychometrics, as well as sample size and how to minimize error.
I have one. I'm over here. This is an unfair question of you, and it may be that some people in the audience would want to say something, that some of the attendees. I'm a PIO, I'm a public information officer. I write about science, and I think that the starting assumption of most of us is it was published in a peer-reviewed journal. I'm not an expert. Should I be really should I care about, or should I take it on myself to evaluate a study and determine whether it's worth reporting on? Is it my job to do that, or can I just trust the scientific endeavor to do it for me so that it's published, I'm going to write about it, I'm going to amplify it?
Yeah, no, that's a really good question, and I don't think I have a good answer to it, unfortunately. But let me give you at least 4 bad answers. Does that work? I think, so one of the big secrets in my area of psychology is that people go into psychology because they don't like statistics and mathematics or engineering. So what you're saying, I think, resonates with people who are publishing in the social and behavioral sciences, too. There's sort of a stats fear or phobia, if you will. So one of the things I recommended on that slide is you can ask the investigative team or the PIs or the researchers these questions. So you don't have to say, oh, God, here's a paper, I'm going to have to calculate the power of this, blah, blah, blah. You can ask the people doing the work. Chances are they don't know the answer either because of stats phobia. And I would take that as a cue. Namely, if the investigative team can't answer your questions about the statistical power of the research that they're doing, that should be a red flag that it might not be worth pursuing, unless, again, you're just looking for clicks or something. If you're trying to get at something that is worth sharing with the world because maybe it's reproducible and real and genuine, that's a red flag. Another option, I would say, is simply identify people you trust who can consult with you on these matters. So you're in a lucky position here because I've seen you email people like Dan Simons and say, Dan, what do you think of this garbage paper by Fraley? Should I report on it? And then Dan forgets to drop me off the email and says, no, that's garbage, low power, okay. But you can identify people at your institutions or people you know well, contacts you trust who have some degree of finesse, who you can turn to for these things. Having said that, I think there are also some simple rules of thumb that can be used. And I generally get worried when I'm thinking about rules of thumb because they're often misused or dangerous in some ways. But we have a simple rule of thumb in our own research group, which is in the study of individual differences, that is the differences between people. We might be looking at the differences between personality traits and life outcomes and things like that. We never design a study with fewer than 200 people, and we don't even read research articles that have ends fewer than 200. It's just not worth it. We got better things to do with our time. So you could adopt crude rules like that too, just as a way of weeding some things out. Sorry, that was 3 things, not 4 things.
There are circumstances where 200 subjects are not required for high power, correct?
That's true, right. So power is dependent both on alpha and sample size, but also how big is the effect actually to be detected. So if we're talking, if I was studying a research problem like, sorry, Game of Thrones has been on my mind all week. If I were to let a dragon loose in this room, would we have a higher incidence of burned people than non-burned people? You know, things like that. I think the effect size would probably be pretty big. And we wouldn't need a room full of 200 people to figure out whether that association exists. Yeah, it turns out when there's not a dragon in the room, people remain unscarred, but Daenerys, Dracarys, things like that. So there are some problems in science where the effect sizes are relatively big, and you don't need 200 cases to observe them. Now, I think it's tricky to understand where those situations exist. I have a weird way of thinking about the world, which is I think there are some problems that are really interesting to study because we are blind to the truth. So I don't know much about astronomy, for example. But I assume that there are things out there that I cannot see because I do not have a powerful enough telescope. But that doesn't mean that those planets are small in magnitude or anything like that. I just don't have the right tools. Give me the right tool, and I should be able to observe it, and anybody else should be able to observe it too. The problem is, in my area where we're dealing with human behavior and human emotions, we're all witnessing this stuff on a day-to-day basis. The low-hanging fruit have already been picked. So what we have left to study, to refine, are the things that are more subtle. That means it's not going to be as big as dragon flies into a room, the town dies, right? It's going to be more, 10 minutes left? Okay, I'll stop with the dragon tales. Okay. There are going to be more subtle things, which require more powerful microscopes. We need larger sample sizes to detect those more subtle effects. If we're thinking about something as complex as educational outcomes, how kids perform in a class, it's not just a matter of whether they're using a laptop or not. There's probably 100 different things contributing to that, which necessarily makes the signal relatively weak. You need a way to sort of amplify it. So yes, I'll just say this is a rule. That's one of the dangers of rules of thumb.
Right.
Yes.
Okay. I was wondering if in social psychology or psychology, are the funding rates for studies commensurate with the number of samples you actually need? Because this is an issue we face a lot, I think, in science in general, is that the grants are too small. You have to promise more than you could ever afford to do to get it, right? And then you say, okay, well, I'll just get done what I can. And I'm wondering if there's this, if you guys feel this crunch as well.
So I'm not sure if I fully understood the question. Can you ask it just one more time in a slightly different way, maybe? When you said funding, I got all excited and distracted.
Yeah, right. Do you get enough money to do sample sizes that are big enough to be meaningful?
So I'll just speak from my own experience serving on certain grant panels. I would say, yes, it's possible to get the money you need. Not necessarily, let's say, to follow people across their entire life courses, but to do meaningful research. And I would say also, at least at the National Science Foundation and the social and economic areas, there is more attention on statistical power these days than there was in the past. There's always been lip service to it, but now people are thinking more critically about the proposals. Is this proposal asking a good question? Is it proposing a study design that's capable of providing an appropriate answer? And emphasizing that in a way that I haven't seen people emphasize in the past. So I find that kind of exciting.
I'm wondering whether modeling would help amplify the power that we get from probably a smaller sample size. What do you feel about that?
Modeling?
Yes, computer modeling, and now with more artificial intelligence, we are like amplifying the little data that we have.
Yeah, that's a good question. The question is, can we use computational modeling to sort of amplify the signal in some of these low power situations? And I think there might be ways to do that. Part of the problem is I'm not clever enough to be able to say how to do that. And because I think I'm an empiricist at heart, I'm always thinking the best solution to this problem is more data rather than more modeling. But I think sometimes if you could start off by modeling the problem, it would provide you with some better constraints on what you might expect to find. And that could be used to guide how you go about designing your research. Because if you're just casting a wide net, that's using a lot of resources in a relatively blind way. But if you can cast that net in a very specific way that might be informed by some sort of computational or mathematical model, that could be a real benefit to the lab, the field, et cetera.
So you mentioned earlier meta-analyses, and I've been noticing more and more of those being published. And as someone who has a strong enough background in stats to analyze my own data, but not something as complicated as a meta-analysis, would you be willing to talk about how you personally look at those to see if you think they're done well or if they're falling into sort of some of the similar traps that you've been talking about?
Okay, so Brent, can I ask you a quick question? Are you talking about meta-analysis later today? No, dang, I was going to dodge that question. Okay, so meta-analysis refers to the quantitative study of published studies or even unpublished studies. It's like studies of studies, basically, for those of you who are less familiar with it. And in some ways, I think meta-analysis is more powerful than sort of basic research for at least one reason, maybe two reasons. One is it necessarily involves working with more cases than any single primary study can work with. So by definition, meta-analysis tends to be better powered than the primary studies that are used to compose it. The other advantage of those meta-analyses, of course, is that they're typically drawing upon samples from a variety of different places. So you get some heterogeneity in those analyses that you wouldn't necessarily get if you were just working with a primary sample. Having said that, there's this kind of joke that I guess comes from the computer sciences, garbage in, garbage out, right? So if you're taking a biased research literature and then meta-analyzing it, the answer you get is necessarily going to be biased also. So it doesn't solve all problems. It's not that kind of panacea. But I do value the results of meta-analysis more than the results of any single primary study for the most part. Now, how can you critically suss out a meta-analysis? You know, there's probably some good resources on that, and I couldn't tell you, I'm just gonna give you my own impressions off the top of my head, which are uneducated and biased in other kinds of ways. But I would say the more studies that are used in a meta-analysis, the better. The more diverse studies there are, the better. And probably the better the sample sizes and the measurement properties of all the individual studies feeding into it, the more trustworthy it is. One danger, I would say, with meta-analysis is because there's a tendency, at least in the social and behavioral sciences, to think in a binary way about research questions, like, is there a difference between these two groups, rather than what is the difference between these two groups? The results of just about every meta-analysis I've ever seen are, yes, there's some kind of difference. And people still don't know what to think about the magnitude of that difference. Now, that turns out to be something that Brent Roberts is going to talk about a little bit later today. But I view that as being one of the challenges for how we interpret meta-analysis. What do we use that information for? That's a problem for primary research studies too, but I think it becomes more clear in the context of meta-analysis because there, the measurement error typically fades away and you just end up with a number and now you don't know what to do with it.
Sorry. Hi.
Hi.
I'm a PIO for a university, and one challenge that I encounter is that I'll talk with a researcher about their findings, which is based purely on some statistical calculation that they've done, and I have a very hard time translating that into findings that the average person can understand. So how do I describe what a p-value is? How do I describe what Cohen's ABC thing is, whatever that is? So as somebody who probably talks about this, do you have any recommendations on how we can take more statistical findings that, let's just assume that they're very relevant and exciting, and translate that for an audience that doesn't understand statistics, coming from somebody who also doesn't understand statistics, but you know, maybe I understand just a little bit more than the normal reader?
I have the perfect recommendation for you. And this is the perfect before lunch recommendation, or is it before break? Before coffee recommendation. This is almost exactly what Brent Roberts will be talking about later today. This time I'm not trying to just sort of dodge the question. I actually think he has some good answers to this question, so I think you're gonna love hearing his talk. As will I. Okay. Thank you very much, everybody.